what we have known about the sigma. So maybe we summarize a little bit before we go further. So in the first part of chapter 4, we talk about the distribution of x bar, right? So we imagine we have a population, okay, and for this population, it has the mean and the variance, which we usually don't know about it. And so we draw a sample of size n, and then we can get the data xn, x1 dot 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 up to xn. Then based on this, we are able to make a guess about the population mean based on the sample average. And this sample average, we know that it has some properties, okay? And the first important piece of the properties is expectation. So what is an expectation? Expectation is the average, and we see that the expectation of the average is the mean. So what that means is if we keep doing this sampling process again and again, on average, this will be a very good estimator, okay? Because on average, the value is exactly equals to the population mean. So remember, the time you calculate the sample average, there will be only one number. But when we talk about sample average as a random variable, we are trying to say we will repeat this sampling procedure again and again. And that's how the variation comes from. And so what is the variation of x bar? Another piece is this. The variation of x bar is equals to the population variance divided by n. And what I mean is the variation of your estimation is going to be reduced when you increase your sample size, and which is a good thing, right? And so if you want to reduce your variation or accuracy of your estimator, you should increase the sample size. And from this, we have another piece, which is the distribution of the x bar, okay? And x bar, if the population is normally distributed, then the x bar will also be normally distributed. And here we fill in is variance and the mean, okay? So what we did is simply make use of the first two pieces of information. And what is new in point number 3 is that we know that x bar is going to be normally distributed as well. So this is x bar, and sometimes we want to calculate the difference of two averages. And in this case, again, we will make use of the knowledge that if the two population, that is the population A and B, are both normal, then the difference of the sample averages will also be normal, and their mean and their variance will be this. Okay, here I want to emphasize again about the sign. So here you can see this is minus, right? So it's natural to see that the difference is also in the average. Okay, it will be also the difference of the population average. That you should be very careful about the variance, because the variation is going to be increased, and that's why there's a addition instead of minus. And so what we have here is things from 4.1. Then last week we have things from 4.2. And so the things that we learn is the confidence interval. So the confidence interval for the mean are these. If the sigma is known, then the confidence interval is x bar plus minus and then here you write down z alpha over 2 and here is sigma over the square root of n. If you don't know the sigma, which means the sigma is unknown, then you will use another version. Okay, and in fact, the two formula are almost the same, okay, except for two places. The first is that you will replace the population standard deviation by the sample standard deviation. Another thing is about the about the z value. You will replace it by the t value, and also you have to take care of the sample size. Okay, because when you check the t distribution table, you have to use something called degrees of freedom. And the degrees of freedom in this case will be the sample size subtracted by 1. All right, and let me see. Do I miss any topics? Okay. Yeah, okay, so that's it. Okay, so this is what we have from 4.2. And the last piece is the 4.3 today. And in fact, I can simply state the formula. Okay, so so far we have been focusing on the population average. But sometimes you also want to know about the variation of the population. Okay, because the variation tells you a lot about the data. Okay, if you see that the variation is a lot, then you will expect, even though you may have a very accurate estimation of the mean, then you will have a very high chance of seeing data that is very different from the mean because you have a large variation. And in short, what we have today is the confidence interval for the population variance, which is this. All right, so this is and so this is our main topic for chapter 4 today. And after this, we will go to the next topic in chapter 5. Okay, now, so here, let's look at the confidence interval for the variance. So how do we come up with the mean? So where do we begin? We begin with this statement. We want to have two values, A and B, such that your parameter of interest can be covered by this range A and B with some probability, right? And most of the time, people will choose the 95% confidence interval as a convention. And so this is the idea. And for the mean, where do we begin? We begin with this. We begin with x bar subtracted by mean divided by is standard deviation, which is the square root of sigma square over n. Then on either side, you put down the z value, right? So this is alpha. So what I mean is now you're going to have two values, z alpha over 2, and here, because the shape is symmetric, it will also be z alpha over 2, but we have a minus. And in between, in this orange region, we say it should be